Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this lecture, and today we are going to turn our attention to a new topic in the fracture mechanics called energy release rate. Okay, so this parameter is a very important parameter. If you recall what I have shown in the table as various parameters like G, K, and J and COD and so on, and this form comes as a first fracture mechanics parameter. Okay, so in fracture mechanics, this is a very important parameter due to its energy approach. Okay, most of the problems in fracture mechanics are dealt with energy approach without much of mathematical complications. And also conceptually, there are a lot of ideas have been developed using this energy release rate. So we will begin this chapter by quoting the English solution. If you recall, during the historical development I just mentioned, English solution gave as the first clue about the severity of the crack. So quickly we will review what is this, then we will get into the energy release rate chapter. So what you are seeing in this slide is, I just enlarge this. So this is an elliptical hole in an infinite plate, and what English has shown is that what you are seeing here is as the sigma max, okay, which is equal to 1 plus 2a by b times the far field stress sigma naught. Okay, that is what he has shown, and this is the sigma yy, and this is sigma x. So you can see that is a variation here. So this is an elliptical hole, which is of the central elliptical hole of the length 2a. Okay, so this is a and this is b. That's what we are seeing. Okay, so what is the importance of this English solution? For a equal to b, yes, circular. Okay, the moment a is become b, then it becomes circular. The maximum value of sigma yy becomes 3 times the far field stress, that is 3 times sigma naught, which agrees with the results given by Kirsch. So Kirsch has shown this already, but the moment it becomes ellipse, then it becomes like that. The maximum value of sigma yy increases without a bound as b by a tends to 0. That means the semi-mirror axis B becomes smaller and smaller relative to A. Then what happens? It becomes like a sharp line, a sharp crack. Okay, so ellipse become a crack in that case, and one requires a newer approach to handle such problem. So why do we say that? Because the moment B tends to 0 in that equation, the stress becomes infinite, like the multiplication factor of sigma naught becomes infinite. So what does it mean? That could be three interpretation you can think of. One is the stresses are very high, even with the small applied load, things can become pieces, fit into pieces. Okay, so such things never happens. Okay, so that is one possibility of thinking. The next thing is, the stresses can be very high, it can exceed maximum, it reaches to an yield stress of a material. That is close to reality. So this English solution gave a very good alertness about the stress concentration at the crack tip. Okay, but it is not practically applicable. That is why it says a newer approach is mandatory. Okay, so with this we will go to the next discussion on this energy release rate. So we will start again with the English solution for the continuity, and then we will carry our discussion further. So this is the same figure what I have just shown. That is from the different page of the book. So I just moved from to the actual chapter here. So this is for an infinite plate with an elliptical hole. English solution for a maximum stresses. There I wrote as sigma max. Here it is sigma yy. That is in this there in that schematic I showed because that profile stress profile was nicely shown in that. So sigma yy max is equal to 1 plus 2 by times of a far field stress. That is sigma. Okay. When B tends to 0, no material can sustain this stress. So that is the kind of an impractical solution this analysis gives. That's why a newer approach is required. Thus, even for a small applied load sigma yy, the above equation tells that sigma yy max will be very large and it would exceed the ultimate strength of the material, which is not the case anyway. Okay, so what can we do? So this is one dilemma. Okay, so what happens? The equation suggests that even for a small load, the crack may grow and break the component into pieces, and that creates a dilemma that is called the Griffith dilemma. However, this is contrary to our observations. Griffith argued that some other mechanisms must be in operation which helps solid to sustain solid forms. So what is that? Similar to surface tension of a liquid, all surfaces of solid are associated with surface energies or free energies. Okay, so what we have to appreciate here is the Griffith's first thought process to bring in surface energy to fracture mechanics to explain this, the crack propagation is the important step. Okay, we will see how it helps. These energies develop because atoms close to the surface behave differently from an atom at the interior of the solid. The interior atom is attached or repulsed by the neighboring atoms more or less uniformly in all the directions. So these fundamental ideas, the people who are dealing with materials, they all know, right? The atom at the surface experiences a different kind of equilibrium as compared to one exhibit in interior, right? So that is why this comes as an explanation. But an atom of the free surface has no surrounding atoms on one side, thus requires a different kind of equilibrium. In fact, atoms on the free surface and the ones below have readjust to form an equilibrium, thereby developing a strain in the material close to the free surface. So this is one way of interpreting the surface energy, an elemental way of explaining what happens in this free surface. Such deformation requires energy and is known as surface energy. So very a simple definition for a surface energy we can think of. Okay. But Griffith realized that a crack in a body will not extend unless energy is released in the process to overcome the energy needed for forming two new surfaces, one below and one above the crack plane. So this is very important point. What he realized is the energy required to create new two surfaces. See, he's not just thinking about crack alone. He's just bringing nicely the surface energy into a crack problem, saying that to the crack itself, if you look at the geometry, it contains two new surfaces. So to create such a two new surfaces, it requires some energy, right? So that is an idea how he interprets. The surface energy of the material depends on material properties. However, its magnitude is rather small, of the order of 1 joule per meter square. So what are the surface energy we are aware of? If you look at for the common materials, you can see that for a copper it is 0.98. Surface energy is denoted as gamma S, which has got a units of joule per meter square. And the other parameter you are seeing is a gamma P. Gamma P is the energy required to cause plastic deformation near the cracked surface. So this parameter we will use it little later, but nevertheless it is related to surface energy. That's why it is shown here. So we will keep it after the Griffith's analysis. We will get into the Irwin's analysis of the crack problem. We will use this gamma p. Okay. For example, if you look at the surface energy of mild steel, it is 1.2, and if you look at the gamma p, it is significantly high. Okay, so it's a ductile material. So the energy required to cause a plastic deformation near the crack surface is very, very high. Okay. So for aluminum alloy, it is 0.6 and the gamma p is 4000. Interestingly, Griffith was working on glass, so you see that the surface energy is 2.3, which is significantly high as compared to the other metals, common metals. And then you have the interesting value for ice, and the diamond is the highest surface energy, right? So what we will now do is we are going to review some of our old ideas. I mean, whatever we have already learned. Okay, we are going to look at the elastic strain energy, energy stored in an elastic body when the load is applied, strain energy stored in a linear spring. See, we are going to talk now about strain energy, and we are also going to involve a surface energy to explain the crack problems. So all this, some small definition will come in very handy, and also the associated mathematical simple expressions to explain the energy of this crack formation and so on. So that's why we are going to look at it. So these concepts but we'll just try to understand it for the completeness. So this is a very nice animation for a simple spring pulled in one direction. The load P is applied in this direction, and then you see that load versus displacement plot. And what you are seeing is the strain energy of this action is given by half P delta. So why it is half P delta? Because the load is gradually applied. Okay. If it is not gradually applied, it is a P delta. Okay. So then it becomes like this. Since gradually applied, it becomes half P delta. So you have to remember that. So we can look at the strain energy stored in a body when only a normal stress is acting. So this is a three-dimensional cube kind of material, and which is being pulled in this x direction. So the sigma x is a normal direction, normal stress. And how to write this change in strain energy? It is du is equal to half. Here again it is gradually applied. Sigma s is a normal stress, and dy and dz is the area on which this is acting, and this is a displacement. So what you get is half sigma x epsilon x dv. So this is a volume. Okay, so strain energy change per unit volume. That is how you will get finally for all this small basic definition. And now we will look at the strain energy stored in a body when only a pure shear stress is acting. So this also is very familiar to you, this one. So what is that expression for a strain energy? This is nothing but du again 1 by 2 into tau xy dx dz. This is the area on which the shear stress acts, and this is a displacement, okay, shear strain. So you get half tau xy gamma xy dv. So this is the strain energy stored in the material due to shear stress. Strain energy stored in a member when all the stress components are acting, both normal and shear stress. Then the expression becomes like this. Okay, this is a one equation which explains all the stresses, and then we can now substitute these strain components in terms of stress components. Then we can use this generalized Hooke's law, and this generalized Hooke's law also you all familiar. We have spent enough time on this. We are recollecting all of them. So the strain expressed in terms of stress. So it gives a three-dimensional picture and is also called generalized Hooke's law. So we will be using that. And again, the strain energy in terms of, shear strain, and in terms of stress components, we can write it like this. And I'm not going to spend much time on this because all these things are very simple equations. You already know that, and our aim is to just to get into the some kind of what kind of energy, strain energy formulation appears, what kind of expressions you get. That is an idea. So if you look at the strain energy in terms of applied load P for an axially loaded member, so like this, see, all these expressions are applicable for the slender members in an applied mechanics or strength of materials language. So slender members means what the cross-sectional area is much smaller than the other dimension, the longitudinal dimension or something. So these expressions are used to describe the the energy terms or strain energy stored in a small bodies. Okay, so that's how we should look at it. So in this expression, what is that you are getting? We are getting the strain energy is half into integral over 0 to L and P square by A to dx. So this is all a very simple thing. And what you have to remember is, you see that what kind of formulation is finally we get for the strain energy is U is equal to half sigma square by E. So we will remember this. So this is one expression we are going to keep on using it as long as we are using this strain energy concept. And this is for the torsion, member subjected to torsion, and this strain energy is calculated by this shear formula. This kind of expression we have seen it in the torsion test, and where MT is the moment of torsion and IP is the polar inertia, right? Moment of inertia, which is all given by the strength of materials books and small equations, and then you get this final expression like this. And we can also recall our flexural stress. This is a flexural formula, again given by the strength of material concepts, and what you see here is sigma x is equal to bending moment of bending moment into y given by Iz. So this also we have used actually. So if you write for the strain energy expression, then again you get this simple formula. So all these small formulas will be handy if you can recall, and then we can apply to this slender members. That's our idea. So now what we will do is we will look at the energy release rate G preliminaries. This is a parameter defined by energy approach to characterize a crack tip. And energy approach has an advantage that one does not have to account for a large stresses that are developed in the vicinity of the crack. Energy method avoids analysis close to the crack tip. Energy approach can only be used for conservative systems where there is no energy dissipation. Energy release rate is primarily developed only for brittle materials. So these are all the points are important to keep in mind, because the energy release rate is going to give a conceptual idea and it is not going to be very accurate. That is why we are saying that it avoids analysis close to the crack tip, because the crack tip stress and displacement fields are very complex. We will see in the later section how the expressions are derived and then how it is useful. Then again we will come back and relate those stress and strain displacement fields and try to relate to the energy. That's a Uh, that's what we will do at the end. But then right now we will just look at energy release rate as a concept which is used only for the conservative systems without energy dissipation. Okay, so that is the idea. So what happens when, what are the changes in the component when the crack advances? Very important idea. Okay, so that when the crack advances, the stiffness of the component decreases. This is very common sense. Okay, if the crack length is keep on increasing, obviously the stiffness of the component will decrease. And the strain energy in the component decreases or increases. So this statement is, we will now qualify for this by looking at small simple experiments, which we are going to show in next few slides. Strain energy in a component may decrease or may increase. So we will look at them in detail. The points of the components at which the external loads are applied may or may not move. So we are going to look at the strain energy aspect for a constant load as well as a fixed grip. Okay, so we will see work is being done on the component by these forces. The points move. Energy is being consumed to create two new surfaces. Okay, so this is an important step or a conceptual step put forward by Griffith by us. I mean, approaching the crack problem by try to define or try to get an expression for an energy release rate. Okay, so we will see one by one. So what is that we are seeing here in this slide? We are going to see a strain energy as a function of load and displacement, like we said in the previous slide. But the first experiment is at constant load. So what is that you are seeing? This is a double cantilever specimen, which is one lever is fixed on the grips, and then which is having the crack length A, and there is a rope over pulley, and then the load P is applied here, which is a constant load. And this, for this experiment, this load versus displacement plot is shown here for the crack length A. Okay, you should ask, why are we interested in conducting this strain energy experiments for a constant load and constant displacement? Because in fracture mechanics, make the mathematics very simple, and these kind of approaches are done. Okay, we will just see how. Okay, so there is another test we are comparing here with a different crack length. This is a similar specimen, but what you see here is the crack length is A plus dA, and that is why the load also has slightly come down from this level. So you can see that. So the crack length is A plus dA. So for this, again, you will see that load versus displacement, it's going to be below this curve. So this is for the crack length A, and this is for crack length A plus dA. Okay. So now what we will do is, now we are trying to slowly increase the load from P to P1. Then you can see that already the crack is growing, and then as the crack grows, you can just watch this P1. The dotted line is its original direction, but then the moment the crack length increases, the P1 tries to come here. I will just play this. Yeah. So now the crack length becomes A plus dA. The P1 has just started from here and then reached this curve. Then it will follow this curve because the crack length is becomes A plus dA. So what is that we are trying to understand from here? So now we can look at the strain energy for these two systems. The first case, there is I mean the crack length, the initial crack length which was there in A plus dA, the strain energy is given by this triangle, and the earlier crack length was A, so the strain energy is given by this triangle. So that's what we are trying to now see. So strain energy is given by delta U, that is this triangle versus minus this triangle. So you can write it like this: delta U is equal to half P1, because it's a constant load, that's why it is P1 into V2 minus P1. So V2, this is this triangle minus this triangle. So you can see that this triangle is much bigger triangle than this. So obviously this will become, so this is, what is this triangle? This is a truncated triangle, is the change in strain energy between these two events. Okay, so change in free energy is shown in this triangle. And what is the net result? The net result is the strain energy of the system increases. So as the crack length grows in this cantilever beam experiments, the strain energy increases. Okay, so this is what it is given. But what is the external work done? External work done, because we are applying the external load, constant load. So the external work done is given by this red rectangle, because the moment you start changing the load from P to P1, then this line moves and jumps to this another line, the load displacement plot. So this area under this curve is called external coordinate. So we will play the animation once again just for the clarity. Yeah, this is load versus displacement data for this, and your second experiment, it is A plus dA, and now you see that load is coming down, then it transfers to the next one. Then this is the strain energy for the second experiment, and this is the strain energy for the first experiment. The change in strain energy is this one, what is the truncated triangle, and which is given by half P1 dV. That means the strain energy of the system increases. The work done is P1 dV. So now we will look at the same experiments for the constant displacement. Okay. So what is constant displacement means? It is the specimen is kept under the fixed grips. Okay. So the fixed grips, the crack length is A, and if you look at the load versus displacement plot, something like this. And then again another second specimen with the crack length of A plus dA, again kept at fixed grip, and there is no external load here. Please understand, it is a fixed grip, so the energy required to move the crack comes within the system. Okay, that is the strain energy that we will discuss now. So what is that we are seeing? Again the same thing, the load, the stiffness of the second specimen, which is having a higher crack length, obviously will have the lower stiffness. That's why it is like this. And now you see what happens as the crack length, I mean if they increase the load, if the crack started moving here, then the crack length becomes A plus dA, similar to the previous experiments. It is just coming down. Okay, the load is coming down because the crack length is increasing, the load is coming down. Okay, so you can see that it reaches a P2, and then we can write similar expressions. So what one important point you have to remember is, as the crack advances, no external work is done in this case, because they're all kept under the fixed grip. Okay, on the system, because the external load is not allowed to move. Okay, so that is one important. So that means external work done, W, delta W is equal to 0. But strain energy, if you look at, delta U, that is change in strain energy, by this, the difference between the area of these two triangles. Okay, so this is a, if you look at the change in strain energy is much smaller truncated triangle compared to the previous one. So in this case, for a fixed grip experiment or constant load displacement experiment, the strain energy of the system decreases. So in one case it was increases for a constant load, the other case at constant displacement it is decreases. Okay. So what is that we are going to say now? For a general loading, okay, that means both constant load and constant displacement, you can write it like this. Okay, in the limit when delta P tends to 0, that means this will become 0 or this will become, delta V becomes 0, this will become 0. If this becomes 0 and this will become 0, then what happens? The quantum of energy, okay, whether the constant load or displacement, the quantum of energy available for a crack extension is the same. Very important point we need to remember. Okay, whether we use constant load or constant displacement, the energy available for the crack extension is the same. So that is what's saying here. The first case strain energy increases and in the other case it decreases. In practice, any general load displacement behavior can be thought of as discrete steps of constant load displacement. So you can see that this is like, you know, it's a constant load displacement, constant load, constant displacement kind of small steps are conceived as a general loading. Okay, so in a general load we just consider it like that. So what happens is strain energy in the presence of a crack could be arrived at based on dimensional analysis or a relaxation analogy or actual calculation based on the crack face displacements, but it requires knowledge of stress and displacement fields. So like I mentioned in the beginning of this lecture, right now we are not looking at the stress field at the crack tip or a strain field at the crack tip. We are looking at the trying to explain the energy, you know, arrive at an expression for energy release rate based on the energy concept. Okay, so we will look at it. How do we do that? For a central crack, that means a crack with the two tips, the strain energy is given by UA. U means a plate which is or a component having already a crack of length A. So the strain energy is equal to pi sigma square A square by E. So this is a expression for the strain energy of a plate containing a crack. Okay. This result is for a crack in an infinite panel of unit thickness. So this is also important. So right now we assume that all this strain energy calculation is for the unit thickness. Otherwise, there is another term will come to this expression. Okay. What we will now do is we have to now see how do we derive this. How this analogy is relaxation analogy is envisaged. So consider this schematic. This is a plate of thickness B, and which is being stretched. Okay, so we can think of, you know, when I say the plate, you may think that's a solid plate, and especially we are talking about a brittle materials only. Just for our, you know, understanding, we can just think of an elastic strip which is being stretched and then, you know, sealed here in a stretched condition. You can think of that situation, which is also true for the, you know, brittle solid. That is the actual thing we are discussing. But to understand the you know, what we are referring here, we can think of some elastic material here, and then now introduce a crack at this center. So what happens? This is a crack, and the crack is appearing as an ellipse here, elliptical hole. And what is this two triangle which is shown? Which is the, you see, this is a strained region. Okay, it could be of any dimension, but for simple schematic to just get an idea, we are taking this triangle because the mathematics is simple. So you assume that this is height is 2a times lambda. Lambda is proportionality constant, and the crack length is 2a. Okay. Note the area on which the strain energy is released. So what we are saying is the two new surfaces are created here, and for that creation of the energy, the energy comes from the strain energy region from this place, because there is no external load applied here, because it's a fixed grips, right? It is all already fixed. The spin was fixed, and then we introduced a crack here, and then the two new surfaces were created. And for creating that two surfaces, new surfaces, the energy comes from this nearby region. That is how we should assume at this point of time. This is simple schematic. Okay, so we are trying to make some analogy. So if you take UA into volume of the two triangles, what just we have witnessed, into sigma square by 2E. So that is how we are going to calculate the UA. Okay, this expression we have already seen. 2 times this, because it is a two surfaces, and then the thickness of the plate is B, so you get this expression like this: 2 lambda A square B into sigma square by E, and lambda is pi is equal to pi by 2 for thin plates. This also we will correlate in the later derivation how we justify this. So all this, I would say the symbols are quite unique for fracture mechanics. So you have to keep that in mind. B is for thickness. Lambda is it's a proportionality constant here. It's not normally we use that for wavelength and so on. So you have to be little alert to get into this kind of symbolism. So we get this strain energy UA is equal to pi A square B sigma square by E. Okay. So now what will we do? Now we look at variation of surface energy and strain energy in a fixed grips for a constant displacement. Okay. Because that what we have looked at is one side. We are trying to take the other ideas into our discussion. So that's why we are starting this. If gamma S is the surface energy per unit area of one surface, the surface energy required for a model of thickness B, which is equal to US is equal to 2 times 2A into B gamma S, which is equal to 4A times B into gamma S. So we are bringing the surface energy down. So we are trying to do a energy balance, right? Okay. So for that, what is that we are trying to do here? Energy versus crack length plot we are creating, and this equation is nothing but a straight line equation. So the energy is increasing with the crack length. So it goes like this. So this is a surface energy for a fixed grips, and from the relaxation analogy we got this expression like this, which is UA is equal to pi A square into B sigma square by E. And then what is that? This is a straight line, and what is this curve shows? This is kind of a square. So that means parabola. Okay, a second degree curve. So the net is something like this. So the net total is UT is equal to US plus UA. Okay, which gives a curve like this. That means it gives a maxima. It gives the maximum. So what does it mean? It demarcates this curve into two segments, and which is very, very important conceptually. Why it is important? Because it gives or it indicates a new parameter called critical crack length. Okay, it is AC, incremental crack growth by crack growth mechanism, and catastrophic crack growth by fracture mechanism. So what we have to understand here is, when we talk about energy release rate, we are talking about energy for the crack to grow incrementally. Okay, that is delta A. What is the energy required for the crack to grow incrementally? Okay, so that is what it is called, incremental crack growth by a crack growth mechanism. So we have looked at several crack growth mechanisms, but any one of the crack mechanisms can involve in growing the crack to a AC. So it gives a very important idea that critical crack length. The idea of critical crack length is provided by this relaxation analogy concept. Okay, basically this energy release rate concept. So catastrophic crack growth by fracture occurs after this critical crack length. So very, very important idea to keep in mind. We will bring this, we'll keep this idea, and then we'll bring it again as we just progress in this discussion. Okay. So what we are interested in is the incremental change in the crack length to occur. The incremental energy requirement should be satisfied. We are trying to do energy balance, and this all the analysis is meant for a brittle material. So the dou U A by dou A is equal to dou surface energy by dou A. That means what? Here the change in energy as a function of crack length is equal to change in surface energy as a factor. This is a kind of energy balance we are trying to do, and then if we can rewrite those expressions what we have got, we can write it like this: pi sigma square 2a by E is equal to 4 gamma S. And if you differentiate this equation with respect to 2a, and then you get this expression. Why we differentiate with 2a? Because 2a is the crack length. Okay, so the final expression is pi sigma square a by E is equal to 2 gamma S, and then you can rewrite this expression like this: sigma into square root a, which is equal to square root of 2 E gamma S by pi. Okay, very, very important equation as far as the energy release rate is concerned. And most of the textbooks also write this equation like sigma. The A will be inside the, A will be right hand side inside the square root. So we can verify this expressions in the subsequent discussion. How it was verified?